Okay, so let's get started. Welcome everyone to the Topos Institute Colloquium. Today we have Christoph Benzmueller, who Dana Scott recommended that we invite because of his great work with proof assistance. So please, Christoph, whenever you're ready.
Yeah, thank you very much for the invitation to present this work here. It's actually kind of survey I'm going to present of works we've done over the last decade. And the title gives you an idea of what I'm after, logico-pluralistic exploration of theories with computers, particular foundational theory. So the focus will be on making logics negotiable themselves in proof assistance systems. And well, the long-term motivation is very well captured also by this quote of Leibniz. If we had a characteristica universalis, we should be able to reason in metaphysics and morals in much the same way as in geometry and analysis. And well, I don't believe that we are on the way to finding a characteristica universalis, a universal logic at an object level, but I think that eventually with distinguishing in proof assistance systems between meta and object logics, we can get a bit closer to this long-standing dream of Leibniz to have machinery supporting reasoning in very different areas of application. And as usual, this is not an own work. It's heavily based on collaboration with colleagues, with students, and the main part of this presentation in particular with Dana Scott, who is in the audience. I saw that. Hi, Dana. Let me give a brief overview of what we're going to dive into. First, I say a bit more about my research motivation, and in particular, depict the methodology and framework I'm going to use, so make that a bit more clear and present. Well, we don't have so much time, so it will be rather abstract in the presentation. And as we said, if you have questions, we can interrupt. And I may have to skip then some parts, but I have nothing against questions on the fly. Well, in the main part, you see then, after we have discussed the methodology, which I call the LogiKEy methodology, which is based on an approach to universal meta-logical reasoning. The meta is very important here. We then dive into studies where we use that methodology for exploration tasks. For example, an exploration task here in category theory that was based on a free logic that we embedded in classical hierarchy logic. I come to that. So you see here the negotiation of the logics we are working with. In the main part of the talk, we will be looking into free logic, and these studies were suggested actually by Dana and were conducted together with him. I mentioned at the very end, depending on time, some further highly relevant foundational studies, deeper studies in metaphysics and in ethics and law, because I think that work now in particular might be useful also in the context of trustworthy AI, but that might also be subject for discussion later on. So in order to understand my personal motivation better, or my personal standpoint, I want to give you briefly my working definition of artificial intelligence, because I'm here in the field because of this kind of deep intrinsic interest in the question of whether there's a significant difference between humans and machines. And therefore, it's very important that I briefly depict you how I currently see artificial intelligence being defined in my own working hypothesis. So of course, we have to distinguish generally between weak AI and strong AI. We all know that. But I think if you ask about strong AI, you need to think about different levels of capabilities that actually have to interact in order to get further in direction of explaining what strong AI could possibly mean, if possible at all in machines. I'm still kind of skeptical here. So first of all, it's about problem solving in the sense of weak AI. So we build systems that can play chess or Go. it's about exploring and acting unknown territory, thinking about the Mars rover here, for example, where you have to have agency, perception, planning, and so on. But the more interesting levels for me are these levels 3, 4, and 5, namely abstract and rational reasoning. So how can we get systems to a stage where they can explore new theories, for example, in maths or in metaphysics, and so by eventually pure thought experiments with little data, eventually no data to start with. How about these capabilities of humans to self-reflect, to, for instance, detect own mistakes, to question own results, to eventually then, based on these kind of questioning of own results and own behavior, to reshape own value systems and so on. And that brings me to the fifth layer, namely social interaction. So the capability to adjust own personal goals that are very important for how I behave in life, and also eventually interact with all the other layers in a direction so that they adjust to the values to a community, for instance, for achieving a greater good. And at the moment, we are building systems mainly at the lower layers, and we use a lot machine learning technology. And I think for really convincing solutions that also include these higher levels, we need more than just machine learning. So that's my personal position. And I think that we need to dive further into integrated research. So where we really look into hybrid systems that combine symbolic and subsymbolic capabilities in AI systems. And you see here some of the buzzwords mentioned that are very nicely depicting how contrasting the pros on both sides at the moment are. I don't want to dive further into that right here, otherwise we lose too much time, but it's actually this year what I think that is needed to get to a next level of AI systems. Also a next level of AI systems in direction of trusted or trustworthy AI. And when it comes to symbolic AI and the role of representing objects, I'm very much on the side here of a recent article and recent opinion pointed out by Wolfgang Biebel, German AI pioneer here from the very beginning. Many of you might have heard his name or know him. And in this article that appeared, unfortunately, in German in Informatik Spectrum, he talks about, or he brings the attention to what he calls representing objects. So abstract representations that have been objects of study in computer science, and in particular AI, from the very beginning. And if you think about it, then representing objects are not only key to symbolic AI, so logical representations, but they also can be experimented with in the computer. This is exactly what I will show you later. That's what we do. They, in a sense, you could argue now, become partly physical, accessible. One could even now question whether they, by this becoming physical and accessible, become part of nature. So we shift here boundaries eventually between what we typically call experimental and the boundaries between experimental natural sciences on the one side and then sciences of the mind on the other side. Symbolic AI and logic in combination with computer experimentation on such representing objects, therefore, I think deserves increased attention as an experimental science, and it deserves increased attention in terms of these higher levels I've depicted earlier on in my working definition of what artificial intelligence means, or at least strong AI means. And examples of such representing objects we see when we explore mathematical theories, how we work with them, how we reshape them, or metaphysical theories or legal theories. And what I want to point at is that in this talk, I'm particularly also interested in manipulating, exploring the underlying logics that come together with these theories at abstract level. So what we will hear about in these presentations are experiments we conducted, experiments of the form that we were interested in shaping or formulating a particular argument, a particular theory, assessing it, And in order to do so, we turned it into representing object, including a representation of the logics, the logic layer that is relevant for the theory. And then we conducted experiments in the computer. And this, of course, then informed again our original assumptions about the theory and so on. So that went then on in circles that you will see presented later on. And originally, I started doing such experiments where also the logics were negotiable in the area of metaphysics. So in the area where we looked into small arguments in metaphysics, in particular here, the ontological argument for existence of God. So that was many years ago. You probably saw some of these headlines this work created. That was unfortunate. I have to mention it here again. It's a bit funny story and also sad story because, you know, originally in that interview with Spiegel, I gave about the results of these experiments, I was asked what kind of computer systems, supercomputer systems, presumably, we used in these experiments on the computer side. And I said, well, there's no supercomputer needed. I just did it on my MacBook. That was not clever to say MacBook instead of notebook, because then the word appeared once or twice in this article. But see what the international headlines did with that. So that was still okay here on the original Spiegel article. The English version was also still okay, but then you see how these headlines changed. So, is God real? Scientists prove his existence with Gödel's theory and MacBooks. Researchers say they used MacBooks to prove Gödel's God theorem. And then God exists, say Apple fanboy scientists. Well, this is clearly fake news about what we did. And apparently this journalist here never even read some of our papers at the time properly, or neither talked to us directly. It was all about just, you know, headline creation, typical stories you see every day nowadays, unfortunately. So what we really did is we assessed an argument via such experiments, going round and round through experiments. And the results of these experiments are presented in papers. We published them at EKEy conference, at IchKEy conference, at the German AI conference. And these were results, including interesting new observations. For instance, the inconsistency of Gödel's original version, the 1970 version of Kurt Gödel on the ontological argument. So we detected that inconsistency, which was fixed in the very end by Dana Scott, that he presented in 1972, but he fixed it for, unknowing that he fixed an inconsistency, it looked more natural to him to change the definition in question. I don't want to go here more deeper into the details. That's not so relevant for what we do later. But now, you know, we didn't stop here with the first round of experiments. I continued over the years and then also compared the variants by Kurt Gödel and by Dana Scott to others. For instance, those proposed by Melvin Fitting and by Anderson. And I used ultrafilter theory to look at the positive properties, which is a relevant notion in there, and then conducted comparison studies using the methodology we are also using later in category theory. And using then this approach, comparison approach, where again, we negotiated at the logic level, we came out with further interesting insights, which finally led now recently to simplification of that argument, which again can inform, I would say, even attack the original variant by Kurt Gödel, because it's an implied simplification that, to my impression, is might not be even too simple, but it needs to be further investigation by folks now from philosophy and theology, I guess, and reaction on that, and further studies to eventually come up with emendation. So that is one area where we conducted such studies here, where we went over various rounds of reshaping theories and rerunning experiments and making logics negotiable. And the methodology behind that we call it now LogiKEy in a recent article that was published in Artificial Intelligence. So the idea really is to only fix that meta logic. And in fact, even this can be replaced, if you want so, by an even more expressive meta logic. So here we take classical higher order logic, Church simple type theory. Why? Because we have already very good proof automation and interactive theorem proving support for it. And it's expressive enough to go very far, as you will probably see with the different works I mentioned in the remainder of the talk. But even that layer is in principle replaceable, but then you have to replace the entire machinery we are using, because that is the fixed part. And for that fixed part, we then have proof assistance systems available. So that makes it rather interesting to stick with one such meta logic, at least for some time, to have one common environment you always reuse for your experiments. But then everything on top of that is negotiable. So in that meta logic, we then formulate via shallow semantical embeddings of these logics, the object logics of interest. And these object logics, free logic, you will later see, is then used to formulate a domain-specific theory or domain-specific language, which you then use in certain applications. For instance, such comparison studies as I just mentioned. And the two layers, the two lower layers here, the connections of the object logic and the meta logic is well depicted in this article, Universal Metalogical Reasoning, Recent Successes, which ultimately goes back to joint work with Larry Paulson, where we showed how quantified multimodal logics can be embedded shallowly in simple type theory. But now, the studies I mentioned, they started, for instance, with a higher order modal logic. So exactly this work that was done with Larry Paulson, an extensional higher order modal logic, on top of which we then formulated a theory of positive properties, which was then needed or used in order to formulate Gödel's ontological argument. And you see later, we switched then in these works I mentioned, where we did the comparison studies from the extensional higher order modal logic to a little bit richer setup, where we also could talk about intentionality better, or better distinguish between extensionality and intentionality. Now we could play with the assumption or with the idea to study whether the notion of positive properties should be an extensional or intentional notion. And we could play now better with that notion by having this richer object logic at hand. But that was needed then to switch to a richer logic setup on the yellow level here. And to formulate then, for example, for the comparison study, ultrafilter theory based on top of that, and then conduct assessment study for variance of Gödel's ontological argument. In other areas, we are currently working in, for instance, in legal argumentation and legal reasoning or normative reasoning. We recently worked with a modal logic of references suggested by Johan van Benten and colleagues. And on top of that, we formulated a value-oriented legal theory, which we then used for an encoding and assessment of very prominent legal court cases discussed in the literature, so-called wild animal appropriation court cases. You find that reported in these papers here. And in the remainder of this talk, we will focus now on free logic as an example on this yellow level. Some of the papers relevant are mentioned here on the left. And on top of this free logic layer, we are going now to axiomatize category theory or explore axiom systems for category theory, with the idea also of assessing them in the end and compare them with other suggestions in that direction that were out there in the literature. So that brings us to the final slides, to that introductory part. These two lower layers are enabled by what I call this universal metalogical reasoning approach, which addresses this quote here by Leibniz in the sense that we say, well, maybe there is a universal metalogic in which you can do a lot in terms of talking about other logical systems, which you then use for your modeling exercises. And the way that works, here's an abstract slide, is we are after identifying the logic in red, the object logic now here, as a fragment, so to say, of the logic in blue, classical higher order logic. If you dive into the papers, you find that worked out in more details. For example, for quantified modal logic, for intentional quantified modal logics, for deontic logics, and so on. So the very idea is that we provide a set of equations that give you an interpretation of the logical connectives of the logic you're interested in, the object logic you're interested in terms of the meta logic. So local unfoldings and compositionality are then properties that you easily get if you have such an elegant set of equations, which you can then expand to unfold your definitions, the definitions of your quantifiers for the logic in red. And we don't go for a deep embedding where we would introduce the logic in red as an inductively defined structure, for example, and data type that we introduce, because that would it's interesting, and many others also do that in the system. We can also support it, but typically that has problems in terms of proof automation. Then many proofs actually turn out to become induction proofs. So we have gone quite far with using shallow semantical embeddings, and I continue in current work to follow that line, but also to consider in some circumstances to switch to deep semantical embeddings, or even both. So here's a slightly different picture now, turning the things around. The meta logic is now on top of that picture, and the application is on the bottom, what we do. And in the context of the ontological argument, we wanted to study Gödel's ontological argument. So we study in metaphysics. We needed modal logics, higher order modal logics, first extensional higher order modal logics. There were no provers available directly for that. And the embedding technique allowed us now to actually reuse existing theorem proving technology for the meta logic where this logic was embedded in, namely Isabelle Hall. Now, we used Isabelle Hall for one particular purpose, or for maybe two or three. But one of the most important purposes is proof automation, because that's excellent in Isabelle Hall. It has access to a tool called Sledgehammer, which again gives you access to a whole bunch of world-leading theorem provers, which again internally work together with SAT solvers. So you see here all the theorem proving systems that are developed over the years are kind of accessible in that framework, and very successfully accessible via the tool called Sledgehammer, which translates into these logic representation and partly translates information back so that Isabelle Hall can verify or reproduce arguments delivered by them. But what is also important, that was this year, is that we have model finders and counter model finders. This is really, really important and very fruitful for such kind of studies as I mentioned, and as I will now show you and dive into a little bit more. If you switch to category theory, the entire infrastructure stays the same. The only thing is that the set of equations that you formulate for embedding free logic in higher order logic changes. And if you switch to an application area like machine ethics, the entire infrastructure is the same. The only thing that changes is the set of equations that you pass on to the theorem prover to give an interpretation of that changed logic in classical higher order logic. So that uniformly supports not only research and applications, that is what we focused on mainly on so far, but it should also provide an excellent basis for reforming or partly reforming education about non-classical logic. So I think one can write textbooks that now with hands-on material in proof assistance very nicely introduce material on various areas of non-classical logic in a very homogeneous setup. And that is not sufficiently explored yet. We should pay more attention to that. So summing up this first part, ontological argument, we had various interesting insights by conducting such experiments as explained, and some of the knowledge we produced was not known before. Now we come to this foundational study in category theory that was suggested by Dana after he saw my presentation in Berkeley at the time, where I presented the way where we dealt with quantifiers in the context of higher order modal logic, in particular the different variations of quantifiers we use. So for cumulative and varying domains and constant domain quantifiers, then he saw that this framework should immediately be applicable to free logic, and free logic would be an interesting basis for exploration of axiom systems in category theory, because he did that before in the 60s and 70s and published about it. So this here's the one paper that was suggested to me then by Dana. I didn't know anything about free logic at the time, I have to say, and it's a shame, but I didn't know about it. Usually you think about Karl Lambert when you, or often when you talk about free logic, but also Dana was very active in this area already early on. You see this paper here from '67. And it addresses aspects of partiality. So free logic is interested to provide a proper foundation to deal properly with partiality and also then with definite description that not properly denote things, existing things. And there have been, of course, proposals out there before, but none of them have been really satisfactory. There's another paper that was recommended then to me by Dana, where again, free logic is discussed in the context of intuitionistic logic. And in there, you also find the proposal then of an application study or an interesting application, namely an axiom system for category theory. And you see here, one key element is now that we explicitly talk about existence. The E predicate here stands for the composition of these morphisms X and Y exists. And you see here the condition. So it exists even only if domain and codomain coincide. So we want to distinguish now better in the logic setup between existing and non-existing objects, and we don't make silent assumptions about existence, and want to better distinguish between, for instance, what free variables may refer to and what bound variables may refer to. So we want to keep, for instance, the notion or the idea of bound variables so that they refer to really existing objects only, and free variables are interpreted more in a schematic way, as Dana writes here, namely they may refer to both existing and non-existing objects. The same for arbitrary terms in your logic. So that can be summarized by these three principles here. You find them in the 67 paper. Bound variables range over an inner domain that we call the inner domain E here of existing objects. And all our objects are belonging or captured by this more general outer domain D, where we have non-existing and eventually existing objects. And the quantifiers only range over this inner domain of existing objects. But if you have free variables or arbitrary terms, then they might refer to objects in the outer domain as well. And of course, principle 3, the domain E might be empty. So we are not making assumptions that there are any existing objects given from the beginning. So this can be encoded using this idea of shallow semantical embeddings in Isabelle Hall relatively easily. So for instance, here, the outer domain D just becomes a new uninterpreted type. Call that type for individuals. And if you want to generalize that, and we in fact did it in follow-up work, you might introduce it as a polymorphic type so that you can give it more structure. But here we started in our first round of experiments just with a type declaration I. We introduce a predicate for existence to actually captured this idea of an inner domain of existing objects. So as an uninterpreted constant symbol, E, you see here how we introduce new syntax. The E is new syntax definition in the system. And then we have eventually we want to have a distinguished non-defined object, an undefined object, and call that star. You see how we introduce that here and say that it is non-existing with this axiom. The interesting thing, in fact, is that while we leave the normal connectives like negation and implication unchanged from the meta logic, so the new symbols you see here unchanged from the meta logic. These are the meta logical symbols in classical higher order logic. These are the new defined ones, so they are just overloaded in a sense. But the changed notion is actually the universal quantifier here, because this is now guarded by the existence predicate. So this here tells you the universal quantifier, the new one we introduce, is just running over the existing domain, which we can express by this formula here by introducing this guard. And we can introduce, that's a nice feature of Isabelle Hall, new binder syntax easily, so that we can write now again formulas with that new quantifier in the usual style for all x, phi of x, right? So that under the hood makes heavily use of our framework that is based on simply type lambda calculus. So lambda abstraction plays an important role here to make these equations work in the background. You can also introduce now definite description operator in terms of that new construction here. I don't go into that. We would need some time for that, and it's not relevant for the studies in category theory. Okay. And yeah, here you have a bit another depiction, eventually more readable. So the essential thing is that we can now introduce these guards now over the existing objects to introduce universal quantification, and we can use that also for the lifting of the introduction of the definite description operator, which I don't explain here any further. In fact, this object undefined and definite description, we forget again. It's not relevant for the studies we do in category theory, which I will depict now. So the experiments suggested by Dana were as follows. He wanted to find a connection from a notion to be discovered or studied or explored of generalized monoids to the axiom system you saw earlier in the 77 paper. And he was interested to explore the relationship of this axiom system to the axiom system proposed by Freyd and Scedrov in their book from '92, Categories and Allegories. And the question here was, can we develop here a stepwise system of axioms that start with the notion of generalized monoid, get to the axiom systems from the 77 paper, and then compare it also with the axiom system of Freyd and Scedrov, and ideally they would all be equivalent. But it turned out to be a question also about the underlying logic. Therefore, it's so interesting to bring that example here in that context. Well, a little bit of preliminaries. I said I don't dive too much into the details. You should get the overall story, and if you want to dive into the details, I have a long list of references in the end where you might dive into, and suggestions for what topic you should consult which papers. But a little bit of context we need. So the morphisms are now object of this type I, as motivated earlier, or we could introduce a polymorphic type, which we did in later works, but let's start here with a type I. And then we can consider composition as partial functions from this type I to type I to type I. So functions over this type I, partial. Codomain and domain the same. Now, two important notions we also need to introduce is clean equality and existing identity. So two different notions of equality, which are motivated by that finite structure we have now D and the subdomain E, and they are needed or were relevant in the context here. So clean equality says X is cleanly equal to Y if X is, so if under the condition that X is existing or Y is existing, we have identity between the two objects. And identity means really identity on the domain D, the outer domain D. And this is an equivalence relation, which you can easily prove with sledgehammer, but this is an easy task even for beginner students, of course. And then you have existing identity, which is defined slightly different. It says that both X and Y are existing and are identical. And it's obvious that this is not reflexive notion of identity, because if you have a non-existing object A, then A is obviously not identical to itself according to this definition. So that means that when we are talking about non-existing objects, for instance, denoted here by the term 1 divided by 0, then we cannot conclude that we have self-identity on so with the existing identity on that objects like 1 divided by 0. We also cannot say that the present dead object, which is the present king of France, is self-identical. Also, this cannot be inferred by that system. Well, this is very interesting. Then you see that already for addressing some issues in the modeling of mathematical aspects or mathematical challenges that include partiality. Now, that was the study suggested, and here are the axiom systems as we explored them on the way. So starting from what we see as a generalized notion of a monoid with closure conditions and talking about identities and associativity here, down to the axiom set that Dana proposed in his 77 paper. And we proved all of these equivalent. So this axiom set 4 was equivalent to 5, to 5, and 3 to 4, and 2 to 3, and so on. And we proved that in the system using the sledgehammer tool. Only here we were able in the system to prove only one direction, namely the direction from 2 to 1, but not from 1 to 2. That is because here's this columnization step involved, and that changes models. And this is something we haven't got our hands on yet in the system, but needed a metalogical argument to make sure that everything is okay here with the transition step. Well, I could dive now a little bit more into these explorative studies. I have slides prepared, but depending on the time, because time is running, I can only dive into some highlights of that study. You got the idea, I think, that we proved these mutual equivalences and so on, and had to solve several questions on how to modify this axiom step by step in each stage. You see here that they are modeled quite in the same surface syntax. That is interesting and important for us. So that kept also intuition quite high in the proof assistance system. That's a good feature of Isabelle. And you see here how we conducted these comparison studies, and all these proofs were basically automated on these different layers. What is interesting is that we, of course, studied also features like consistency, whether left or right directions are implied, like here, whether you can avoid here an equivalence statement and just replace it by an implication statement. So these were questions we answered with machinery. We actually explored the notion of this identity morphism predicate in the first stage in interaction with the machinery. And here's a highlight from the interaction that I want to point at. For instance, there was an email exchange, as we had many on the exploration phase, Dana and me. And I wrote here, well, we were at a stage where we had a proposal for an identity morphism predicate in a prior stage of development. And now there was a new one here. And I said, when we take this new proposal, IDDI, as this one here, and replace ID, the previous proposal in our axioms we currently look at by this new proposal, then I can show that these two are equivalent. See the attachment. So IDD, this new version, because it was a bit simpler, seems to be a suited notion of identity morphism. And Dana wrote back, I'm surprised because I did not see how to prove this idempotency property here. Have to think about it. I think C and D have to be used. Well, I wrote back, no, see my previous email, the attachment C and S are actually used for that by the provers, and so on. So that were quite typical for interactions we had. Or here's another interesting one later in the development stage, because then later Dana gave me an exercise. So in the stage of the current development, which we have here, please check whether we have this here provable. So some property we were interested in. I fed it into the machinery, asked the system by push button, is it provable? And I got a counter model, which I then translated back to Dana, often in such a form. That should actually be done by the systems automatically, but they are not good at that yet. So you get ASCII representations back. And then as a person who is not very into the systems yet, this is often then too clumsy to read off the real intuitive part, or the creative part here, the useful part. And if you had such representations, that would be much better. So I was here the middleman and presented these then in a nicer form, either in such a representation, better already readable as in the system itself, and then often even graphically. And that then informed again the process, because very often these counter models were very interesting. So later in the experiments, we had interesting further observations of that kind. Very often small, minimal counter models, but nevertheless interesting. So for instance, here a model with idempotence, but no left and right identities and so on. Well, but it's not very difficult, but the systems performed very well on in these studies. And then finally, we were able to actually prove the equivalences between all of these axiom sets, and then confirm so this kind of idea of exploring an evolution from a generalized monoid to the axiom set as proposed by Dana at the time. But now, the last 5 minutes on this part, I want to show you what we found out about this comparison with the axiom set to Freyd and Scedrov. Because here, that is now about changing also the logics, or getting to know more about the logical assumptions that make axiom systems work. Because when we looked at the axiom system proposed by Freyd and Scedrov, you see it here on page 4, 8 axioms proposed, and translated them into our representation syntax. They looked like this. And fed them then into the computer system under the same assumptions that under which we investigated the axiom system by Dana from the 77 paper, we got interesting results. So the consistency question was answered first positively by nitpick. Yes, it finds a model, but inspecting that model, I could see that there were only existing objects, or one existing objects, or two, I don't remember exactly. But then, of course, that triggered the question to ask whether there exists also a model when I assume that there is at least one non-existing object. And nitpick didn't find a model anymore, meaning, well, everything is total, so we don't have partial objects here. So that cannot be the idea of that axiom system. So something was wrong here. And in fact, when I, under the assumption that there exist non-existing objects, I can prove falsity from these axioms in this particular setting, as explained before, so the free logic setting. And the problematic axioms are also pointed out by the theorem provers, so you know exactly what to look at. Well, we then experimented with the axiom set, and comparing axiom A1, or looking at axiom A1, you find that in Dana's case, you have existing identity instead of clean equality used. So I just replaced, or it was obvious to replace clean equality here by existing identity. And if you do that, then you can in fact prove that this axiom set 6 here implies the previous axiom set 5, the 77 axioms by Dana, and vice versa. But you also find redundancies reported by the theorem provers. Namely, either you can omit the A4 axioms or the A2 axioms. So lean back again. Is that really meant? Probably not. So maybe Freyd and Scedrov, as we might assume, working in algebraic theories, assumed that free variables range over the existing objects only, and not over the existing and non-existing, as in our framework here. Well, but we can test that as well, because remember that we have these universal quantifiers defined, that range, whose range is restricted over the existing. So we can quantify over these formulas and replay our experiments. Now we get consistency, confirmation also for the case when we assume that there's non-existing objects. However, none of the axioms by Dana are implied in that context. The model finders give you counter models. If you want equivalence to Dana's axioms, you need to explicitly add the strictness conditions. So we learned something again, namely that here the strictness conditions on domain, codomain, and morphism composition are assumed or are mandatory to make that work. Well, looking at the book itself, that was not really mentioned in there. I tried to find the discussion of strictness or non-strictness. So that means you have to assume strictness conditions to make that work. But that is a rather strong assumption on the logic side, I would say. And strictness cannot, in that framework, when your variables range only over the existing, easily be expressed. So I don't see a way how you would formulate that. So in a way, I think that is a reason why eventually the axiom system proposed by Scott based on free logic gives you a clearer picture of the idea here of what a category on this axiomatic level is. We also did the comparison study with the proposal by Saunders McLean, the seminal paper here, and also under the same assumptions of adding strictness conditions and having explicit quantifiers introduced. So to restrict the variables only over the existing, we could show that they are equivalent to the axiom system by Dana. So again, to this system in the free logic setting. And we have that all published in the archive of formal proofs if you want to see more details about that. So I think I have to get soon to a conclusion statement, and I have a few pointers I want to give you in the remaining minutes. So first, let me summarize the results here of that study. So it was quite obvious that we had here a rather interesting, successful story, rather on an entry-level exploration of category theory, but nevertheless interesting because it pointed to these logical peculiarities of the developments of these differences between the axiom systems. And we found minimal axiom systems, dependencies, the theorem provers. They told us about consistency or inconsistencies. We were pointed at strictness assumptions, and in the end, we ended up with a very clear picture of how these axiom systems are related. Methodologically, we had evidence for the LogiKEy methodology, now in a completely different area to the ontological argument for the existence of God. And we were quite surprised by this high degree of automation and the good response by the model finders and counter model finders also in this particular work here. But unfortunately, the required familiarity with Isabelle Holl is still too high. So it's not the case that Dana or any other expert who has never worked with Isabelle before would easily, enjoy such an experience in the interaction because it's still kind of a very steep learning curve about the technicalities of such a system, which is getting better and better, but it's still there, we have to admit. So how about digging deeper? We conducted further experiments. There was a bachelor thesis by Luca Tiemens, who studied modelloids in his master thesis project, which later led to a publication here, a joint one. We had a master's thesis project that looked at intuitionistic multiplicative linear logic, so a fragment of linear logic. Now developed on top of that level of category theory, which is a very interesting story. You start with classical Haider logic, then free logic, then an axiom system for category theory, in which you then again formulate foundation of such a logical system and get even a moderate level of automation out of that on that level. So quite interesting, chicken and egg question you introduce here, starting with logic and then you go to categorical foundations and again to a logic. We also studied more the practicability and the elegance of the approach in this master's thesis project by Jonas Bayer. And here's a slide he recently presented that gives you some idea of additional things he looked into based on the same axiom system that Dana proposed in his 77 studies, with a few changes. I mentioned that you have to introduce polymorphic types and so on, and there are questions about type classes or whether you at some stage would like to have dependent types. Well, the last minutes I want to spend into pointing some further other interesting foundational studies we conducted, much bigger than what I reported here. Namely, for instance, this work here, a study on the Principia Logico-Metaphysica by Edward Salter. So he's working on that since, I think, nearly 30 years now, or since the 80s when he published his book on abstract objects. Since then, he's developing this theory together with colleagues. Now, Daniel Kirshner joined at a certain point, or I tried first, but that ended up then in a PhD thesis project of Daniel Kirshner. And since 5 years, they have been collaborating since 2016, roughly, on that project here, where the idea was, can we put the foundational logic that Edward Salter is starting with, which is an intentional logic, it's an at least second order, in principle even full higher order modal logic he starts with, but it has a focus on relational type theory as opposed to functional type theory as a basis. So it seemed relatively distant from classical high order logic, and in this regard already was a challenge for us, not only because it was such a big piece of development, but also because of the logical foundations and the gap we had to face between these assumed logical foundations. So the object logic was for us a real challenge. But in his thesis, Daniel shows how you can overcome this gap. And then again, start with the metalogic whole to help exploring this foundational theory. And in the course of this study, which is meanwhile, the PhD thesis is continuing, but it's defended meanwhile, but the work is continuing. So at the moment, it's 24,000 lines of code in Isabelle Hall using the methodology I've shown. And it has some highlights. So for instance, Daniel early on in this work rediscovered a paradox that Ed thought he got rid of already by taking some precaution, but Daniel showed him that this paradox was still there, deeply rooted and not easy to see. And in fact, it was this interaction with the theorem proving assistant that made it feasible to discover that and explain it so that it could be fixed and could lead then to an adjustment of the theory, not only the theory, but also the underlying logic, in which then shifted more in direction of a free logic. And you see, this kind of development of this theory in the last 6 years was significantly now influenced by such kind of experiments as I reported on. There are some early publications on that, but the work in Daniel's thesis goes much beyond of what we have discussed in there. The sources can be found online, and eventually, if you want to have a look at this thesis directly, write him. It will probably take a little bit until when it's officially published. Yeah. So there are further foundational studies, which I can just mention because I have to come to an end in topology by, for instance, another PhD student, David Fuin-Mayor, who, for instance, looked into para-consistent and para-complete logics from the perspective of topological semantics, and yes, further ongoing work. We are very interested in encoding ethical and legal theories. I mentioned it earlier. Some examples of such encoded theories are also available online here in formalization of Alan Giwood's principle of generic consistency. You can find also the source code in Isabelle source code in the RFP. And that brings me to the conclusion. So I think we have seen successful applications of this experimentation cycle. We got new insights from the computer, which led to revisions that often were then only small, needed small changes in the code, in the representing objects, also at the logical level, that's important to remember. Changes may also occur at the logic layer, and then to modified experiments. And you can go through that cycle. And if you have a big piece of work like at Salter and so on, then it can be very painful even to check the tiniest change in your logic or in your axiom system, of course, as we all know, by pen and paper methods. And by these methods here, that can speed up the process significantly. So that is what I presented, an approach that actually makes also the object logics negotiable, and this is very fruitful. And we have applied it to a range of different object logics, to different object logic combinations. I haven't been talking about that yet. Different application domains, including some very relevant one, I think, when we come about the encoding of norms and ethics and laws for instance, computer systems in the future. Good performance of theorem provers. Even more valuable is the model finding capabilities with systems like NitPick, and in Isabelle Hall, when we apply this approach in Isabelle Hall, these are all benefits we get in particular in there. We also have very good syntax representations. This is what we did. This is what we not yet did. But what I would like to do in the future, to just parse to the theorem, so that's a dream, right? To parse an argument or a theory to the computer and let it explore the logic under which this theory works itself, or amend the theory and amend eventually the logic so that you get back a revised version fully automatically explored by machines. I don't think that this is feasible in the very near future, but at least stepwise, we could think about what would be needed to make that possible. This is my last slide. I think I leave that just as it is, and open, take questions if you have some. Thank you.
Thanks, Christoph. Okay, any questions? We have time for just a few. So feel free to raise your hand or just unmute yourself if you have questions. So Seth, maybe you have a question? Looks like Seth has his hand raised.
I have to see whether I can see.
Seth, feel free if you can speak.
I can't hear you yet.
No, I can't hear him either. Maybe I'll ask a quick one while Seth is trying to get his microphone working or whatever the issue is. So you said that there's a steep learning curve. I had two questions just about Isabelle and that learning curve and LogiKEy. But first, the basic one is, can you do dependent types in Isabelle Hall? And second, but either way, is the learning curve high for people who know a little bit about Lean or Coq, or is it high for them also, or just for people who've never worked with a theorem prover before?
Okay, so there are no dependent types in Isabelle. There's something like type classes, which is not as expressive as dependent types, but maybe one should have, in order for this discussion, look at a paper recently written by Larry Paulson on type classes and dependent type theory. So as I remember, there was a paper out there which discussed that in particular context. So that is eventually, and this is a question I'm also still interested in. So when do I come to a stage when I really see the urgent need for introducing dependent types in the encoding of some of these logics? And I think we had some indicators that this could actually ease certain things or make them more elegant. And I think the person to contact here is Jonas Bayer with his latest work in category theory, where he eventually can point you to some interest in the further development of these applications of the category theory axioms where there could be a need to switch to such a system. But so far, in all of these experiments, we could avoid dependent types. So, well, we stayed in Isabelle. But of course, I mentioned it, you could switch to another system and then work with one that has even a richer underlying meta logic.
Right,
now,
but then you
the
wouldn't
other
get,
question,
yeah, you wouldn't get
the
access
other
to these sledgehammer and nitpick and that sort of thing if you were somewhere.
Yes. So I mean, there's so wonderful systems at the moment being built, and I don't want to make too much of an advertisement here for Isabelle Hall. They just have these wonderful, highly developed tools already inside. The others are also providing means of proof automation, and maybe they are catching up soon or have done already. So I mean, I've been working now for a couple of years, and as usual, if you have started with something, then you stick to it for quite some time. But that brings me to your other question. I think, for instance, for me as an Isabelle user, it's not so hard to switch to any of the other systems. So you know so much about the general environment. And of course, over the years, you have also learned a bit about the other logic in theory, so that shouldn't be too much of a problem. So I think that any person that has worked deeply with one of the current proof assistants out there shouldn't have a comparable learning curve at all to a complete layman starting with those. And therefore, in my group work at university level, I always make sure that I form groups of interacting students so that at least one already ideally has some background knowledge about such a system. So in particular, when you do what I do in courses with on an interdisciplinary level, then you want to have one computer science students who knows how to handle the systems interacting with a philosopher who knows about the theories you're interested in. And this interaction then works out quite fruitful, and both sides learn a lot from each other.
Okay, thanks. That's helpful. I'm going to see if Seth can unmute and try again. Seth? Okay, that doesn't seem to be working. So any more questions? If not, let's thank Christoph.
Oh, okay. How's this?
Oh, it works. Wow. Okay.
Yeah.
Hello.
Yeah, great. Okay. So the issue is pertaining to your study of in the first half of the talk and the application of formalization to areas particularly like law and morality. What the issue is that in these subjects of culture, there is inconsistency. In fact, for example, I've heard the view expressed that the skill of a lawyer is to understand how law is inconsistent and then use the inconsistency to the advantage of the client. So
Well,
could
yes.
thanks about this issue.
Yeah, there is. We could dig deeper into this objection, because one of the works we looked at, these are the papers that are called value-oriented legal reasoning, something with that in the title. There we actually looked into these animal court cases, so these wild animal appropriation court cases. And they are not easy to model, because you here seemingly also have an inconsistency if you not take value systems into account. So there's one ruling which, when you look with very coarse-grained classes, is in conflict with another ruling. But if you then take value systems into account and you guard your knowledge base with respect to that value system, then you can explain away the inconsistency and you can say something, well, this is a conservative judgment, or this is in this case it was different, right? So then you suddenly have another layer of aspects that you can take into account to distinguish between, for instance, then apparently inconsistent rulings. But I think what you are pointing to are eventually real inconsistencies that are exploited and eventually made even into a business by certain lawyers. But I would say that if we had machinery which could pinpoint such objects or such aspects, and really, I don't know, make them objects objects of study with computers, this apparently undesired aspect of law could eventually be gradually eliminated.
Great, thank you for that. We should probably end it here, and so let's thank Christoph again.
Yeah, but thank you for having me. That's I enjoyed.
Yeah, it's great. So we'll stop the live stream, and